Black holes with exceptionally large masses over a million times the mass of the Sun, known as supermassive black holes, SMBHs, are commonly found in the universe today. Nonetheless, their origins, as well as the specifics of when, where, and how they came to be over the course of 13.8 billion years of cosmic evolution, remain ambiguous. Research spanning the last several decades indicates that an SMBH resides at the core of each galaxy, and its mass is almost always about 1,000th that of its host galaxy. This close relationship implies that galaxies and SMBHs have co-evolved together. Revealing the origin of SMBHs is thus crucial not only to understand SMBHs themselves, but also to elucidate the formation processes of galaxies, the major constituents of the visible universe. A key to addressing this issue lies in the early universe, where the time elapsed since the Big Bang, the beginning of the universe, was less than 1 billion years. Thanks to the finite speed of light, we can look back at the past by observing the distant universe. Did SMBHs already exist when the universe was only 1 billion years old or less? Is it possible for a black hole to acquire such a large mass, exceeding 1 million solar masses and sometimes reaching billions of solar masses, in such a short time? If so, what are the underlying physical mechanisms and conditions? To close in on the origin of SMBHs, one needs to observe them and compare their properties with predictions from theoretical models. To do this, one first needs to locate where they are in the sky. The research team used the Subaru telescope at the top of Mauna Kea, Hawaii, for the present study. One of the biggest advantages of Subaru is its wide-field observing capability, which is particularly suited for this purpose. Since SMBHs do not emit light, the team looked for a special class called quasars SMBHs with shining outskirts where the infalling material releases gravitational energy. They observed a wide sky area equivalent to 5,000 times the full moon and successfully discovered 162 quasars residing in the early universe. In particular, 22 of these quasars existed in the era when the universe was less than 800 million years old, the most ancient period in which quasars have been recognized to date. The large number of quasars discovered has allowed them to determine the most fundamental measure, called the luminosity function, which describes the space density of quasars as a function of radiation energy. They found that quasars were forming very rapidly in the early universe, while the overall shape of the luminosity function, except for the amplitude, remained unchanged over time. This characteristic behavior of the luminosity function provides strong constraints on theoretical models, which could ultimately reproduce all the observables and describe the origin of SMBHs. On the other hand, the universe was known to have experienced a major phase transition called cosmic reionization in its early stage. Past observations suggest that the whole intergalactic space was ionized in this event. The source of the ionization energy is still under debate, with radiation from quasars being considered as a promising candidate.